Okay, so good afternoon to all again, and thanks Ami for giving the opportunity. Okay, so in this talk I'll be talking about a very special case of a radical membership problem. The outline of the talk is as follows. First, I will define some objects that this problem will require us to work with, namely varieties, ideals, and radicals. Then I will state the problem, so that we'll be looking at. Then of course we'll be looking at some motivation why the problem is important, or why to study it. Then I'll be presenting an algorithm for a special case for it. So this will be the topic of this particular talk. So the main theorem, and then we'll be looking at some application in polynomial identity testing for a restricted class of depth-4 circuits. So it will have some implication for PIT, and actually the motivation to study this particular problem also came from that case of PIT, depth-4 PIT. Finally, I will I will state an open problem which you can think about, and that will be it. Okay, so let's begin. Let me first define what is a variety. So to save time, I've already written this. So say you are given k polynomials, and for this talk the field will be the complex field, so field of complex numbers, and variety of a set of polynomials, say f1 to fk, which are given. I will say what given means, but for a set of polynomials f1 to fk, the variety is defined to be the set of their common zeros. So the set of points on which all of them vanish. And so here is an example. So if you take the set of polynomials, let's say xy minus z comma z square, then what are then what is this variety? We want z square to be 0, which implies z is 0, and then we want xy minus z to be 0, but z is already 0, so it implies either x is 0 or y is 0. So this set of points can exactly be represented as union of if z vanishes and x vanishes, or it so happens that z vanishes and y vanishes. So it's a union of these two. These are also varieties, as you can see. So it's a union of these simpler varieties. So if you will draw it in the real space, it will look something like this. It will just be the union of the x and y axis. So it will be this. Right? So these two lines are the axes are this variety. So note that this is a union of vector spaces. So you can split this into simple varieties. Okay. So the next object that we will require are what are called ideals. So given a set of polynomials, say f1 to fk, the ideal generated by them is just the polynomial combination of all polynomial combinations of these polynomials. So you are taking coefficients as polynomials and then adding them. So this is what is called ideal. So one thing that you can see is that how does this relate to the variety of f1 to fk? Clearly, if there was a point A in the variety, what does it mean? That all fi's vanish on A, then every polynomial in this ideal will also vanish, right? Because every polynomial is just some fi times hi. So all of them will also be 0. So what does this mean? That this means that if f is in the ideal, then it must vanish on the variety of the defining polynomials. So this implication is trivial, right? Everyone can see this. But one can ask the question that when does the converse hold? So can we say something about if we are given a polynomial f which is in the which vanishes on all points of this variety? Can you say something about the membership of f in this ideal. Oh, so if f belongs to the ideal, you say that f is a member of the ideal. Okay, this is okay. All right. So to answer this, so this is not, of course, the reverse implication is not true, and I mean it's trivial to observe that. For example, take the ideal which is defined by x square. So what is this ideal? This is the set of all polynomials where every monomial. So this is set of polynomials where each monomial, basically all polynomials divisible by x square, right? So, but note that this implies that x doesn't belong to this. X doesn't belong to this ideal because x is not divisible by x square. But still, you would see that whenever x square vanishes, x also vanishes. So this statement is true, but this statement is not, right? So reverse implication. So to correct this, or sort of, I mean, get a equivalence, we see what are called radicals. So okay, so you can define the radical of such an ideal. So a radical of this ideal is nothing but all polynomials such that some power is also in the ideal, right? So you can write some power of f, doesn't matter which power, some power of f as summation of hi fi. Okay, so in this particular case, although x was not in was not in the ideal x square, you could take x square and then it will be in the ideal. So this would so what this means is x is in the radical of x square, right? From this definition. So here you do have the equivalence. Again, note that if there was a point A in variety of f1 to fk, then on this point every polynomial in the radical also vanishes. Why? Because again f to the e is some summation of hi fi. So if all fi's vanish, then f also vanishes. So but in this case the other direction is also true. So okay, so what does this imply? This implies that if f is in the radical, then f must vanish whenever all fi's vanish, right? So what so this is what is written, exactly this, right? So what Hilbert's null Stellansage, which is I don't know, some I mean a well-known theorem in algebraic geometry, what that says is that here the other way also too. So every polynomial which always vanishes on every 0 of f1 to fk must be in the radical, right? Okay, so what this gives is, this gives sort of an radical membership. So you can say, when does it happen? So what is radical membership? So let me just so what basically this says is that f is in the radical. So this is the same notation. So f is in the radical if and only if it vanishes on the variety. That's what it means. Okay, so let's come to what problems we can look at when we are dealing with these objects. So the first problem is, of course, ideal membership. So in this problem, you are given black boxes to these polynomials, a set of polynomials. Okay, black box, or you are given them, you are given circuits for these polynomials. Some way you are, I mean, they are given to you. You can query the evaluations of these polynomials, and you have to test. You have to decide whether this polynomial is in this ideal. This is ideal membership. Analogously, you can also define a radical membership. which asks, which asks whether f is in the radical of this idea. From null and such, this problem can also be rewritten as whether variety of f contains the variety of f1 to fk. Right? Just now we saw that. So these two, I mean, these are just different formulations. Okay, so let's see why to study this problem and why is it important. Okay, so one thing that we can note is that, of course, the problem that we will be looking at, we will be given f, and I mean all these polynomials will be given to us as black boxes. Of course, so you should be able to decide identity. If you cannot even, I mean, give it a point where the f, I mean, if f was non-zero and you cannot even tell whether f was non-zero, then of course you need stronger things than that. So before studying this problem for some circuit class, it's better to first devise identity testing problems, and then you can ask this stronger problem. Okay, so what is the complexity? So here's the question. What is the complexity of radical membership? Okay, so let's start with the simplest case, in which degree of all given polynomials yeah, that's what I mean. They can be given to you as a circuit or a black box. I mean, some black box access. You can query the polynomials on your choice of points. Okay. So the degree of let's consider the simplest case in which the degree of the given polynomials is 1. Okay, so let me just, I mean, so in particular you are given this problem. Okay, this is the simplest case of this problem. So in this problem, I mean, is equivalent to saying just whether L belongs to. Okay, let me just write it and. Right? Okay. Why? Because such ideals actually are called. Okay, so this holds. Okay, so in the linear case, this is very simple. It's just asking whether some given polynomial is in the span of some other polynomial. So this is just linear algebra. Okay, so this problem is I mean, you know that this problem is not difficult, that difficult. Okay, so now you can ask the same thing. What if you allow the defining polynomials to be, let's say, of degree at most 2? So the polynomials can have degree 2. And what I claim is that, so if the degree is at most 2, your degree is 2, I mean, then this can encode co-NP, even for degree 2 case, if you are allowing degree 2. Okay, so let's see how. So suppose you ask a question. So take L to be, let's say, I mean 1. So variety of 1 is nothing. It is never 0. 1 is never 0. So this is phi, and you are asking whether phi contains variety of q1 up to qk, where these are quadratics. Let's say quadratics. I will only consider degree at most 2 case. So what this means, whether this is empty or not. Okay, till now it is okay. All right. So so what the point is that you can encode. So let's try to encode 3 sat in this way. So the point is that first, so you are given a 3 CNF. Let's say it is C1. So the variety that I will form is, first I will ensure that my satisfying assignments only take Boolean values. So I will just put these quadratics. This will ensure that any solution to this variety is on Boolean values. Then I will put Q1 up to Qm, where Q1 will correspond. I will tell you how to construct Q1, where Q1 will correspond to C1 and Q and so on, and every quadratic will correspond to some clause. I mean, one clause each. So without loss of generality, let's say your clause was so this 3 is enough. There are only 3 variables. Okay. What I want is, I want a quadratic such that it is 0 whenever this clause is satisfied. Okay. So basically, I can encode the truth table into this quadratic. So what does that mean? Or in other words, so I want this to be 0 whenever this is satisfied. So this should be 1 whenever this is not satisfied. Okay. Otherwise, this is 0, 0, 0. All right, and rest. So how many constraints are here? There are 8 constraints. But in a quadratic, how many coefficients are there? This is a quadratic on how many variables? 3 variables, and degree is at most 2. I'm allowing 2. So there are 5 choose 2 degrees of freedom. So you can always solve. I mean, this is a system of linear equations, right? Every constraint will give you a linear equation, and this is a homogeneous system. So you can always find an appropriate quadratic. So these problems can encode very. I mean, even if you allow degree to be at most 2, these can encode very strong problems. I mean, this problem can be very difficult to solve. Okay, so. Yes. Okay. And as if these were knots, then you change the truth table accordingly.
Take one to one variation, x1 square and x1 are linearly dependent. So it's not really that maybe you feel, but it doesn't matter.
There are enough degree of freedom.
Yeah, you need to encode a little more. I think you have to do this.
Yeah, never mind.
No, but for 2 you can encode. Definitely, it is certainly true. Okay. All right. Yeah. So the point is that in these type of the point I wanted to make was, it is known to be, I mean, QNP complete. Even if there was a problem, believe me, there are quadratic which can encode. So anyways, the point is that these problems can encode strong problems, and there is a very clear difference between linear case and non-linear case. This is the problem, that whenever you go to something non-linear, things change drastically. Okay, so now that you know what is radical membership, I will just say what we will be seeing in this talk. Okay.
For ideal membership, it's like X space complete.
Yes.
For radical membership, is there better than that?
I think it is P space. I think it's P space complete. I'm not sure, but certainly it's.
Okay.
Oh. Yes. You can reduce quantifier eliminate. I'm sure that it's in P. I mean, I'm not sure if it is in a smaller class, but it's certainly. You can encode quantifier. I mean, you can encode certainly polynomial hierarchy using just in this machine. All right. So the problem that we'll be looking at is, or the things we'll be looking at is this. So let where these are homogeneous of degree d. And d prime. Okay, so consider these consider homogeneous polynomials with some degree upper bound, some d prime, and we want to, and so the claim is that such that each qi, all these polynomials. So okay, sorry. Okay, and so I've just written the factors of p, that p can be factored into polynomials p1 to pd. Qi can be factored, each qi can be factored in their respective factors, and the degree of these factors is let's say at most r. So you are given a degree upper bound. Then also then if the number of such polynomials k and these degrees are constant, so for example quadratics or any constant degree polynomials, they can be, and the number is also constant, then you can decide a membership of okay. So suppose you are given black box access to P and QIs, then you can decide the membership of P in the radical of this ideal, of the ideal generated by Q1 to Qk in sorry. Okay. Yeah, so we are looking at a very special case of a radical membership. I mean, yeah. If you did not bound k, then that example shows that. I mean, it's not reasonable to assume an efficient algorithm because I'm allowing arbitrary degree. I mean any, let's say quadratics, and what I'm allowing is that P should be factorizable into polynomials of some bounded degree. So for me also, R will also be bounded, but can be quadratic. Okay. So yes, this is homogeneous. Yes, even if that was homogeneous, let's say that in the ideal, I mean the whole point is that even for homogeneous polynomials, you don't have degree bounds here. The problem arises when you, okay, so okay, it will be clear. Let me just present. I will present this algorithm, but let me first present some algorithm. It will be very inefficient, but let's just look at some algorithm to decide these kind of memberships. Okay. It's yeah. So it's something like n to the r to the k. Okay. All right. So okay. Sorry. K and R. So so where does this come from? We can. It's reasonable to ask where does this model come from. So I will be talking about this at the end, towards the end of the talk. So so there. So you can consider PIT for depth-3 circuits. So they are sigma k circuits. So what is this circuit? It's just a product of linear polynomials, and there are k such surfaces. And you want to do PIT for this model, okay? So so there is a very efficient PIT, and there was I mean there's an exponential dependence on k, but I mean for constant k it's polytime, and this started from this work of Dirichlet-Pilka, and then Kayal Saxena gave an algorithm for a PIT for the efficient PIT for this in the case of finite fields. Then there was this rank bound conjectures, and there was a long line of work, and finally due to Saxena and Sheshadri there is an efficient algorithm for this. So the next step can be, so this is a depth-3 circuit, so you can ask the next question, what if you have a depth-4 circuit but the bottom fan-in is bounded? So these are still, it's the same model, it's just you want a more robust proof. You want robust techniques in the sense that it should just be robust in the degree of these allies. That's what I mean by robust. So you can ask the same question, what if these are quadratics? I allow one more degree. Quadratics or any constant degree. I mean, can you do PIT for this? Oh, thanks. So can you do PIT for this? So let me just repeat for people. So there was a long line of work for depth-3 circuit. It looks like this. There was work started by Dirichlet-Pilka, and now we are asking, just one can ask a slightly general question: what if you want a slightly robust proof? Not slightly robust. You want a robust proof, but the robustness is in the degree of these factors. And here, so we don't know how to do PIT. So we are just trying to look for a robust proof. Again, this question. So you can see that this product is of quadratics or bounded degree. It looks very. I mean, it looks exactly the same structure. So this question is motivated from here. It follows the same approach that this line of work took. And this arises as the first step. So the first step here, again, as I already mentioned before, is regarding, for example, this question would translate as whether you have L1 to LD, and you have to decide whether this variety contains variety of, again, these products. I mean the same question where these QIs are linear. So it is in this particular area it is difficult, but I would say that this is more difficult than that. Okay, so yeah, so this is the first step, and of course the non-trivial part comes when I mean, yeah. So there is more involvement even in this case after this. Okay, so let's begin. So this problem is well motivated, and I will at the end I will say why this problem is. I mean, what is the case of this question we solve? We don't solve this question. I will just say that it solves one case of this. Baby case of this, and but it leads to an interesting question which we will discuss at the end. Okay, so no, there is a K is the top fan-in, and R is the bottom fan-in. You
keep in mind the top fan-in being constant and each QI being quadratic.
Right, exactly. So think of, so as Ampa said, think of top fan-in to be 3 and the bottom fan-in to be 2. That case will, I mean, everything will generalize from that case. At least what I will talk about, it will generalize. Usually it doesn't. I mean, yeah. Okay. Yeah. So okay. Case when yeah, k equals 2 even for sparse. Okay, for this mod. Okay, for degree is constant. If the top fan is 2, then there are. So I will be talk. So the when for the case when k equals 2, this case is solved due to okay. Actually, this paper will also come in later in the case when this algorithm doesn't work. So let's dive into the proof of this. Okay. Okay. Okay, so let me first let's look at a very straightforward algorithm to. Okay, okay, sure, sure. I will talk it at the end, but you at least you can see that the structure is. Can you see the? Okay, this is, so. In this theorem, I'm not talking. In this theorem, I'm not talking about sigma pi sigma circuits. I'm just saying that this will. Okay, this is an independent problem.
Basically, if you have a depth-4 identity, then you have that the first product gate is in the radical of the remaining piece.
Okay.
This theorem will be relevant.
It will be relevant here. So I was just saying that it is motivated from this. I was just talking about motivation. Okay. So this is, but in general, I think, okay, for me this problem itself is interesting. It just happens to have. Okay, okay, okay. Okay, so let's just see a straightforward algorithm for this. So the problem is that you want to decide if this is in the radical of this idea. Okay, so what does this statement mean? This means that whether there exists some power such that p to the e is in the ideal generated by q1 to q. Right? This is the definition of a radical. Now the point is that, and what do we know? We have some degree. I mean, we are given some degree bound. I mean, we know the degree of qi is at most d. No. D. This is a product. This is okay, and degree of p is also at most d, and these are homogeneous. Okay. I mean, p and qi is homogeneous. Yeah, everything is homogeneous. So now the question is whether there exists an e such that this membership holds. Right. So first of all, you might not have any bound on e, and then you have no idea how to approach this. So luckily, there is a bound. So it's called effective. So what Nullsalen says is that there exists any. What effective Nullsalen says is that given the degrees of upper bound on the degrees of this, it bounds. See, so it says that E is at most product of the degree. So it's d to the k. No. Everything I will say is for general. I will now from now on I will not assume. It's only the running time. The algorithm is robust in the sense that it will not break down if you increase. It will only the running time increases, but it's I mean, technique will work. I mean, statements will hold for any degree, just that the running time becomes worse. But in the linear case, you have techniques which don't hold for. I mean, it's a matter of robustness, not a matter of running time. All right. So there's a theorem which is effective null solensage is used to Kolar and also do. So it says that you can bound this degree by d to the k. Okay. So note that these are homogeneous polynomials. So in particular, this implies is that this membership holds if and only if p to the d to the k is in the ideal. So you see where the difficulty of radical membership is coming from. It's even for homogeneous. It's not that simple. Homogeneity only helps in. Sorry. Okay. All right. So we want to test this ideal membership, and these are homogeneous polynomials. For simplicity, let me assume that they are homogeneous of the same degree. Okay. Of course, it doesn't. It's okay. Okay. So. No, for this it was required. In this theorem, for the PIT case, it was not required because you can homogenize. Non-homogeneous. I don't know. I'm not sure. I just whatever problem arises from the PIT, I only considered that. Okay. Okay. No. This bound doesn't require homogeneity. The statement is that if some p to the e is in this ideal, then e must be, then certainly for some e at most this it should also be in this ideal. Okay. So if let's say e to the d minus k minus 2 was in the ideal, certainly this is definitely also in the ideal. So this is the if and only if condition. That's all I'm saying. Okay. So note that this now you can use linear algebra. Of course, the running time will be very bad, but at least this problem has an algorithm now because there's a upper bound. So what does it mean? It just means that there exist some homogeneous polynomials of degree d to the k minus d such that p to the no, sorry, yeah, right. So let's say the degree of p is also d. I mean, I'm just making it simpler. Everything is okay. I yes. Rabinovich, yes. That will make it inhomogeneous. I mean, but you are saying it also works for inhomogeneous.
But I guess right now he wants a degree bound, right?
A degree bound. You are looking for a degree bound.
No, I'm saying for reverse nuclear there is a good.
No, this is this.
No, but the point is that whatever you do will remain exponential time. Here you will get
I will get a very bad running time here.
Using Rabinovich trick. Using the Rabinovich trick? I don't know what's the Rabinovich trick.
1 plus, I mean, is exactly.
but it will remain exponential time.
Yes.
What?
It will remain exponential.
Okay, fine, but it's AM.
For this particular case, not for any important case. Okay, so okay, so we have so what does this imply if this of
So in your case, I think the point is that your proof is key sensitive.
yes yes
Anything else is
It's
key
like the
insensitive.
creative photo itself, but it's very sensitive to the experiment.
yes yes yeah yeah yeah.
That is why it is interesting.
Okay, so you have p to the d to the k equals g1 q1, right? This is if and only if. So know that gi is so you want so basically now it's a linear algebra problem. So if you express gi to be some alpha I m, where m is this is running over all monomials. Of degree of the appropriate degree, so it's d to the k plus 1 minus d, right?
This exponential kind of so many monomials.
Yes, yes. Right? So we can so what this implies is okay, I will this. So so if you have right, so if you have this if you assume gi to be this, then basically you want to say whether there exists a choice of alpha i's such that this holds. So so if you plug this here, you will get linear equations and compare coefficients. So just substitute gi to be this and compare coefficients. So what you will get is you will get many linear equations, and here you will get this huge tuple. Right, so you will get this system of linear equations because you can check that it's. I mean, you will get a homogeneous system of equations. I mean, yeah. So where these will be of course like, yeah. I mean in alpha i's, alpha ij's. So how many of them are there? We have kgi's. Okay, maybe. So we have so how many? So number of. So how many variables? How many alpha i's do we have? We have k times the number of monomials of degree d to the k plus 1. So we have something like. Okay, let me just. Right, something like this. I mean times k. K is constant, don't worry about. I mean k is constant, so it's roughly like this. Roughly these many constants, and the number of constraints is just the sparsity of p to the d to the k, which is like d to the k plus 1 whole to the n. Right? Makes sense? Roughly like this. So the numbers are all. I mean, it's something to the n. So this is very bad. So you can, of course, the n now you can solve this. I mean, if you are given access to this is the n time, right? It doesn't matter. K is constant. It will not. It will not. Okay. 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 So this is very bad running time. So let me tell you what this algorithm, what we will do. So first, I will tell you how to construct maps linear maps. So basically, it will be I will tell you how to construct polynomially many maps. So which basically map. I mean, so if you make this substitution, okay. So I will give you a set of maps, very few of them, and I will tell you how to construct these maps, such that if you replace every xi by this some a times this, so it's like projecting down to only 2k plus 2 variables. Then I will show that this. So if this did not contain, if P did not belong to the radical, then this non-membership will still be preserved. So I will. So if P to okay, so this non-membership will still be preserved. But now note that we have reduced the problem from n variables to k variables, to 2k variables. So in particular, all of them become sparse polynomials, right? So you are given black boxes to p and qi. So in particular, this and these are all sparse polynomials. They have degree. They are on 2k plus 2 variables and degree d. So they have sparsity d to the 2k. So you can interpolate them, and then just use just use this trivial algorithm, which has a running time of d to the k plus 1 to the n. So here your n will be 2k. So the second step is something: interpolate and check and test. So this step requires d to the roughly 2k time, right? No, it's more complicated. Okay, so now I will tell you how to construct these matrices. Okay, so I don't think I will have. In fact, let me just try. Sorry. It's on 2k plus 2 variables. K is constant. Okay, so suppose I will only be talking about the, so okay, suppose V of P does not contain V of Q1 up to Qk. Okay, suppose this happens. So in particular, what that means is V of P does not contain. So what is Q1? So okay, so for simplicity, I will take now Q. This is just 2. This is only for simplicity. Everything I will say will work for any k. Okay. Let's say there is only Q1, Q2. Yes. So what is Q1 and Q2? It looks like Q1 up to Qd, comma R1 up to Rd. Okay. Let's say this holds, and I want to preserve it. So Vp. What this implies is a variety of P. I mean, this is P1 up to Pd. So what is this variety? This variety is intersection of, so this is intersection of these two varieties, right? Oh, sorry. So this is just intersection of these two varieties. What is this variety? This is just union of these varieties. Okay, so just you can just simplify this. Take the yes. Oops, sorry. right? So this variety does not contain this union. So in particular, it does not contain for some ij this variety. So what we will do, but how many such tuples are there? There are only d to the 2 tuples. So what I will do is I will construct such a map for one instance of, so for one non-membership, and now by now you know that how to construct a hitting map for polynomially many copies. By now you have seen such things many times. Okay, so let's just construct such a map for okay, now Q and R. So let me just put, so without longevity, let me call it Q1 and R1. Now note that degree of Q and R is at most R, right? Okay, but still we cannot use that because degree of this is very high. So it's not clear. We will still be using a lot of things. So what I will show. Okay, so for this I will require what is called irreducible decomposition of a variety. So any variety, for example, we saw this case, right? X, y minus z square comma z. This was just so you can always reduce a variety into its irreducible component. So what is an irreducible variety? As you would guess, a variety is irreducible if it cannot be expressed as a non-trivial union of sub-varieties. So in particular, if V is V1 union V2, it should imply, so if V is contained in union, then V must be contained in either V1 or V2. It cannot be expressed as a union of sub-varieties.
So here this containment just means that if I have a pair of, if I have a point on which both Q1 and R1 vanish,
Yes.
I want that to not vanish on this pair.
Yes, exactly. Right. So some point, there should exist some point.
I'm just saying that you can already expand that as a union, right?
You can expand this as a union. Sure. So in particular, this is what is called the irreducible variety. So the claim is, so basically the irreducible decomposition means that every variety, okay, let me just can be expressed as a union of its irreducible components. Okay. Also, so what does that mean? These are all irreducible, and also you can always take union with things which are already inside the varieties. This will just be redundant. So what you can do is remove the VIs which are already, so to just have uniqueness, also no VI should be contained in VJ. Just to preserve uniqueness, and you can show that this is unique. So this decomposition is unique. Okay. So what I will to remove this, what we will use is something called Bézout's theorem. So what that theorem says. Oh, sorry. No, okay. So suppose you have Q1 up to Q K, where degree of Qis is at most R. See, because we are in this regime, we had degree of Q1 and R1 to be at most R. Then what Bézout's theorem says, actually it doesn't say this, but you can conclude from this that the number of irreducible components in the minimal decomposition is at most the product of the degree. So it's at most R to the K, which is constant for us. So what this means, what does it mean? So this thing, this is Q1 and R1. So the number of components here is very few. If these were linear, how many components does it have? One component. It's irreducible. And what this theorem says is that if you still have bound, this is robust enough. It has only r to the 2. I mean, in this case it's 2, but in general it will be k components. So what does this mean? Sorry. Okay, so let this variety this variety be, let's say, h1 up to h. And what you have is this does not contain this, right? So you have then I claim that for all, so what this implies is this statement holds if and only if for all size 4 subsets, R square subsets, of D, this non-containment holds. This is if and only if. Subsets, let me call it J1 up to JR square, V of Pj1 Pjr square does not contain variety of. Why is this? Why is this? This is because if suppose this did contain this, what does irreducibility? So H1 is an irreducible component. So what does irreducibility mean? H1 is contained here. So H1 is irreducible means there should exist at least one of them in which H1 is fully contained. That is the definition of irreducibility. Similarly, H2 is contained here. So it should mean there should exist at least one of them in which it is fully contained. So similarly, if you have union of R square things, it means that the entire thing should be contained in, there should exist some R square size subsets in which this is fully contained, right? So if you say that for all size R square subset this does not hold, then it means that it does not belong to the variety. It's an if and only if condition. But note that now you have reduced this non-containment problem to polynomially many. I mean polynomially many because this is D to the R square, right? There are D to the R square subsets. And now you have to design maps, design a hitting set non-containment map for each of them, and then there are polynomially many of them because R is constant and you can do it. Okay, so basically you have to preserve this. But note that we have made progress because degree of this thing is D to the some constant instead of, it's at least, this is constant degree. This is constant degree, this is constant degree, right? Earlier the degree was D, now it's just product of R square degree to degree R polynomial. So degree here is at most R cube. So this is, this is progress. But still we want the number of variables in the, so where is the, so here you have D to the K plus 1 to the N. But again there is a dependence on N. Although we have made progress that this D has come down to a constant, still there is a N. We have to get rid of the N. Okay, so here is one thing which you can say. I'm sorry about overshooting the time. Just 5 more minutes. So what you can do is, what I claim is that if you take a random projection, actually this is not this is generic. Let me use the word generic. If you take a generic projection to y0 up to y 2k plus 2, we have this map, right? If you take a generic projection to very few variables, then this non-containment is still preserved. Proof of this is I'm not going to present a proof. It's a little bit involved, But just take my word for it that, I mean, you can formally prove it. It's not that easy to prove, but you can formally prove this. Variables, number of fan in. So you have, I'm sorry. So what that means is, so you have this. I claim that if you substitute this by, I mean, some a of y, where this y is like on maybe 6, okay, and so on. If you take a generic projection to very few variables, this non-containment will still be preserved. What this is saying is there exists some projection. I have not described to you how to construct it. What is the probability of it not being not contained? It means there exists. If you take a random enough, it will not be preserved. But know that this says something interesting. What this says is, assume the A's to be some matrix of variables. So think of these aij's. So what is this? This is y1 up to y6, and you have x1 up to xn, and you are substituting every xi by this. For now, these are constants. So if you will construct this, so know that take the projection. It will be you and construct this matrix. Okay, what will be the size of this matrix? N will be 2k plus 2. It will be only on 2k plus 2. D will be, what is the D here? D is the degree, maximum degree of, so let's say degree of this. What was this degree? R cube. So this is R cube. So it is R cube. K is K. I mean, in general, it will be R to the K. I mean, it was just 3 because, okay, so this is K plus 1 and whole to the 2k plus 2. Everything is constant. So this matrix that you will construct is a huge matrix, I mean, in these parameters, but still it is constant. Moreover, if now you think of AIs as variables, what will be the entries of this matrix? They will be polynomials. So these will be some polynomials, let me call them lambdas, of AIGs. And what this theorem is saying is that this matrix is full rank in the sense that, I mean, has a solution. I mean, if you preserve the ranks of the if you preserve the non-zeroness of the minors, you have that map. And note that minors are just, how many AIGs are there? There are kn AIGs, or yeah, two, okay. So there are these many AIGs, and the degree of any minor is constant. I mean, it's a huge constant, but it's still a constant. So then you can just do PIT, and you will get a set of A's. I mean, you will get a set of maps which only at least one of them, this non-membership will be preserved. Okay, so that's the proof. The main theorem is that how to prove this, that there exists at least one such map. That proof is involved, and I'm not going to present it. But let me just address your question, and how does this relate to PIT for depth-4 things? Okay, so suppose you want to test PIT for what does that mean? If this circuit computes a zero polynomial, you can do nothing. If this computes a non-zero polynomial, you want to find a hitting set for this. What this implies is that suppose this non-zeroness came because of a special restriction, and this came because if there exists I mean, so there exists. Suppose there exists some I. Okay, such that if you take the variety of rest of them, so q 1 up to q I minus 1. Okay, let me call them again from the same thing, qk. So if suppose this happened that suppose this happened, then you know that this circuit cannot compute the zero polynomial, right? This is not this is not a zero polynomial. If this was zero, then you could take q to this side, and whenever this side vanishes, I mean it's in the ideal. So this cannot hold. So suppose this condition holds. I mean it was non-zero because of this condition. Then you can just use the same map to reduce it to very few variables and then use sparse PIT. So in this special case, this you can do this. Interestingly, in the depth-3 case, also the first case which was solved satisfied exactly this condition, and the case which was not solved, Amir and Zev, you showed rank bounds, in the sense that what they showed is that if this thing does not hold, then the circuit must be really restricted. It should be a very special circuit. So what they showed was if this does not hold, I mean not them. It was a long line of work by I mean Amir and Duer, Nitin and many people, and finally they showed the best bound is due to Nitin and Shishadri, who showed that the following, that if this does not hold, then dimension of the span of Lij's, I mean over complex numbers, is bounded. If k is order, I mean it has dependence on k, but I don't remember it. It's k square, I think. So this is bounded. So what can you do? So interestingly, you can make a similar conjecture if this does not hold. Let me even go further and give you several more restrictions. Okay, suppose you take this. So if this condition does not hold, then it means that this condition is violated for every such tuple. So it would imply whenever you take variety of P1 Q1, it's I mean this is contained in the variety of R1 RT. I mean if you take any two of them and take the variety, it should be contained in the variety of the third for every such choice of two things. Okay, so you can make a stronger. Okay, let me just write down. Okay, I don't have time to derive the conjecture. Let me just write down the conjecture, which you can think about. So so the conjecture is, so here's the conjecture. So it's basically it's asking for a Sylvester-Gallai theorem for degree for quadratics. So what the conjecture is, suppose you are given m polynomials, m quadratics, q1 up to qm. They are homogeneous. Also you can assume irreducible. And it so happens that for every distinct ij, if you consider the variety of qi qj, it's contained in variety of some qk, some distinct qk. I mean, okay. So suppose this is true for every such thing, then the conjecture is that the transcendence degree of this set must be bounded. So this is basically this is true if QIs are linear, and it's called over reals it's called Sylvester-Gallai theorem, over complex is called Kelly's theorem. So what this question is basically asking you is that can you make this proof, Kelly's proof or any such proof robust in the degree? It's asking for just very similar thing. It's asking for a robust technique, which doesn't depend upon it. So this bound might get worse. That is acceptable, but it should not break down just because the degree increases. It should not depend upon value of degree. It should only depend. I mean, the bound should depend upon degree, not the whether the technique will work or not. Okay, so the interesting part about all these conjectures is that actually Nitin. So in the paper which I mentioned, so you have this. Okay, so you have this circuit, and so B can. So they have an algorithm which gives a polytime PIT if the following condition holds. So if this condition holds, if transcendence degree of this set whatever, I mean, they take this thing. This whole thing is bounded, then you have polytime PIT. So of course, I mean, the case that this algorithm solves, there are many cases which are not contained here, and sure, there are. I mean, I'm sure there are cases which are. I mean, that's the hope that all cases which this solves are not contained. I mean, these are exactly the cases which this solve. I mean, this would solve the problem. So that's it. So you can think about this. So the interesting thing. Let me just make one last comment. What I find interesting about this conjecture is that for the linear case, it requires you to study incidence theorems, and there is a very nice paper by Barak, Duer, Yehudayov, and Wigderson, which solves it's just very nice. So it solves a robust case of gives a robust proof of the linear case. So there the robustness is in the sense that suppose for some tuple this condition does not hold, it should not break down entirely, right? So it gives a very, very, very robust proof, and so so the techniques are very nice. For this theorem, clearly, I think the proof will require you to study at least this much algebraic geometry. So it will be very interesting if you could. It's nice conjecture because it requires you to study both the things. So it's a great way to learn about these two areas. That's it. Thanks.